Let's now discuss elimination second order. We'll do that again by talking about the thermodynamics kinetics, the nucleophile, which again in this case will be a base, and the electrophile. E2 stands for elimination bimolecular E2. It requires a strong base in order to accomplish the elimination reaction. In other words, that base must be strong enough to be able to deprotonate faster than the carbon leaving group bond itself can actually ionize to form a carbocation. So this reaction is a concerted reaction. The proton is abstracted, the double bond forms, and the leaving group leaves all in one step. In other words, we're going to have a transition state. In this transition state, you can actually see what they call antiperiplanar relationship between the base and the hydrogen and the leaving group. The hydrogen here is on the top of the molecule and the leaving group is here on the bottom. That would be an anti-relationship, periplanar, because as we start to form this double bond, it forms a plane. So my base comes in, starts making a bond between the base and the hydrogen. A new bond starts to form between the two carbons, and my leaving group starts to leave. And that's shown here in the transition state. I end up with an alkene. The rate of an E2 reaction is second order, meaning it depends both on the concentration of the substrate and on the concentration of the base. Here in the example up above, I have this alkyl halide, T-butyl bromide. I have a strong base, which is OH minus hydroxide, and I form an alkene. In this case, I have my base abstracting a proton, forming a bond between the oxygen and hydrogen, a bond being broken between the hydrogen and the carbon, a bond being formed between the carbon and carbon, and a bond being broken between the carbon and bromine. And that's my leaving group to finally form my product. As mentioned earlier, the leaving group and the hydrogen must be antiperiplanar. This is also sometimes called anticoplanar. We also have designations for the different carbons that the leaving group and the hydrogen are attached to. The alpha carbon is the carbon where the leaving group is attached to, and the beta carbon is the carbon that the hydrogen that is removed is attached to. So we have alpha and beta carbons. Let's look at the antiperiplanar or anticoplanar arrangement for E2 reactions based on molecular orbital overlap theory. If I look at the bond between my carbon and my proton that is being abstracted by the base, that orbital overlap is opposite that of my orbital overlap between my carbon and my leaving group. This actually minimizes the steric hindrance between my leaving group and my base here when they're in this arrangement. And it also starts to bring together these two inner parts of the orbital so that they can form the double bond. If we looked at that from the Newman projection, what we're going to see is my hydrogen, which is going to be abstracted by the base, needs to be anti to that leaving group. In other words, it must be a staggered conformation, the lowest energy. If we were to have those on the same side, there's a lot of repulsion between the electron clouds of these bonds, and this would be an eclipse conformation, and that's high energy. And so my base and my leaving group tend to repel each other because they're both going to be negative, and that's high energy. When I only have one hydrogen bonded to the beta carbon, this would be the beta carbon, here's my one hydrogen, This is my alpha carbon with the bromine. When I only have one hydrogen bonded to my beta carbon, I can only have one major product. That's because, again, I have to have these in anti-periplanar arrangement. So I put my hydrogen up here, I put my bromine down here. Again, I'm rotating freely about that single bond until I reach this anti-configuration. That results in this case of forming the E stereoisomer of 2-phenyl-2-butene. If I take another stereoisomer, and again, I only have one hydrogen on my beta carbon, I need to abstract those in the anti-periplanar, and in this case, I form the Z stereoisomer. Let's look at another example that illustrates the anti-periplanar relationship that must be in place in order to have an E2 reaction. So here I have a molecule that's an alkyl halide. I have high temperature, which promotes elimination. I have a very strong base, sodium methoxide, so I'm thinking Elimination II. I now need to make sure that my leaving group on my alpha carbon is anti-periplanar to my hydrogen on my beta carbon, and yes, they are. Those are anti-periplanar to each other, so they're all set up to do an E2 reaction, and in fact, that's what you see experimentally. You see an alkene formed, and this is the most stable alkene that is formed based on Zaitsev's rules. If we look at this molecule down below here, I notice that I've changed the stereochemistry now at the beta carbon, and my hydrogen and my bromine are not anti-periplanar to each other, so these two will not form an alkene. However, there is another carbon here, another beta carbon that does have a hydrogen on it. So in this case, I actually form the non-Zaitsev rule product, and it is in very low yield because this is not a stable product. In the elimination reaction of a linear chain alkyl halide, I can form two different products, either the E stereoisomer or the Z stereoisomer. Thermodynamics says that I want to form the most stable product, and if I look at the reaction coordinate for that, what I notice is that the Z stereoisomer, which would be the cis one here, is higher in energy and has a higher activation energy than the E stereoisomer or the trans stereoisomer. So experimentally, we see this as our major product and see this as our minor product. The most stable product dominates. Let's make that same argument. Let's just do it based on Newman projections. If I draw one Newman conformation of my alkyl halide, notice here my two bulky groups are on the opposite sides. That leads to the more stable E stereoisomer. If my two bulky groups are on the same side, that's less stable. That would lead to my Z stereoisomer. The one here on the left, this Newman projection, is more stable than the one on the right, so this is the one that dominates. Notice in both cases, I still have a anti-periplanar relationship between the leaving group and the hydrogen. That still has to be met for an E2 reaction to occur. What experimentalists have found out is that the most stable alkene is generally obtained by removing a hydrogen from the beta carbon when I have more than one choice. For example, if I look at 2-bromobutane, I have two choices here. I have this first beta carbon here with the hydrogen on it, and I have a second beta carbon with a hydrogen on it. I could actually do an elimination reaction with either of those two. However, Zaitsev says that the most stable alkene is the result, and that would be removing the hydrogen from this beta carbon. We could also see this same thing in an energy diagram here, where I take 2-bromobutane. If I were to remove the proton from the N carbon, I get 1 butene, and that's higher than energy than removing the proton from the third carbon in, which would be 2 butene, more stable. Experimentally, we do see the same thing. We see 80% of the 2 butene, and we see 20% of the 1 butene. And in this 2 butene, there's a mixture of both of them, with the cis stereoisomer being in lower concentration than the trans stereoisomer. Let's look at the transition states for these two different products, the more stable and the least stable. If we look at the transition state for the more stable product, meaning the internal alkene, the more substituted alkene, you can see as I start that transition state, I'm starting to make my double bond here, and because it's more substituted, it's more stable, the transition state. In other words, my activation energy is lower than the activation energy for this transition state because it's less stable. It has less substituents as I'm starting to form that double bond. Let's look at a couple examples of elimination reactions, and let's look at the product mix that's formed. If I start out with this alkyl halide and I look for beta carbons so I can see which hydrogens could be abstracted, I see that here's a beta carbon with 2 hydrogens, here's a beta carbon with 3 hydrogens, here's a beta carbon with 3 hydrogens. So I have several different options here in doing an elimination reaction. However, we know from Zaitsev that the more stable alkene is going to be produced. In fact, that's what we see here. I see that this 2-methyl-2-butene, which is a tri-substituted alkene, has a 70% yield. And if I look at the di-substituted 2-methyl-1-butene, I see 30% in my product mix. And so based on Zaitsev's rule, that all makes sense. This is my major product. It's more stable than my minor product. Another thing that comes into play when we're doing these is the number of beta hydrogens. So here's my alpha carbon with my halogen on it. Here's one beta carbon. It's got 2 hydrogens. Here's another beta carbon. It has 3 hydrogens. We're still going to look at Zaitsev's rule because I want to form the most stable alkene. However, there is more opportunity because there's 3 hydrogens out here and only 2 hydrogens in here. So it is not as dominant as you might predict because I have 3 hydrogens. This one is a di-substituted alkene. I see 67% yield, and I see a mixture of both E and Z stereoisomers. And in this case, I see a 33% yield of the least stable one, even though I have more hydrogens to remove with my base. Our models that we're using to predict the product mix in an elimination reaction are based on stability. And sometimes we have to look at more than just substitution. We have to look at other factors. One of those is conjugation. So for example, if I look at this reagent right here, it's an alkyl halide. I have a beta carbon here with 2 hydrogens. I have a beta carbon here with 1 hydrogen. I could do an elimination reaction to do both. If I look at the 2 different products, I notice this is a di-substituted alkene that I formed. This one actually is a tri-substituted alkene, but it's the minor product. That's because this double bond is conjugated, meaning it's one away from another double bond, and that means stability. I could draw a resonance structure in this case. I could not draw a resonance structure in this case. Therefore, the more stable product is formed even if it's not more substituted. If I look at this example down here, I have another, here's my alpha carbon, here's one beta carbon, here's another beta carbon. If I take off this beta hydrogen, I'm going to form a tri-substituted alkene. If I take off this beta carbon, I'm going to form a di-substituted alkene. However, It's actually benzylic now. I can draw resonance structure. So in fact, this product is more stable because it's resonance stabilized than this product. So we think about substitution, we think about cis and trans, and we think about allylic and benzylic, resonance stabilized structures. Whenever we talk about an elimination reaction, we also need to consider that at the same time it's in competition with a substitution reaction. So we have to consider our reactants carefully. In this case, you can see that I have two options here. I could either attack my alpha carbon and do a substitution reaction, or I could attack my hydrogen and have an elimination reaction. So this methoxide anion can act either as a nucleophile or as a base. However, this happens to be a tertiary alkyl halide, and there's just no room for that nucleophile to get in and attack that carbon to do an SN2 reaction, so it prefers to do an elimination reaction. It's easier, if you will, to go and react with one of these beta hydrogens than it is to attack this alpha carbon. So elimination predominates. So the order of reactivity is tertiary alkyl halides react faster by E2 than secondary and faster than primary. Primary tend to undergo SN2 reactions. As usual, we're always going to predict the most stable product, and for most cases that's going to be my Zaitsev product unless I'm allylic or benzylic. We have specific names for some of these elimination reactions. This one happens to be a dehydrohalogenation reaction because I'm removing a hydrogen, the hydro, and I'm removing a halogen, so we tend to call this a dehydrohalogenation reaction. It's just the E2 reaction that we've been talking about. A strong base abstracts a hydrogen as the double bond forms and as the leaving group leaves on the adjacent carbon. Tertiary or hindered secondary alkyl halides give good yields and do not undergo SN2 side reactions. There are a few things that I can do to actually alter my product mix in an E2 reaction. One of them is actually changing the base. So if I look at this reagent right here, my alkyl halide, I can either abstract these two green hydrogens or I can abstract any one of these blue hydrogens here. And this right here is actually a very small base. So it can either abstract any of those, and it's going to abstract the green ones preferentially because it forms the Zaitsev product. We often call this non-Zaitsev product the Hofmann product because Hofmann, he actually did a series of experiments with what we're going to call bulky bases. You can see this is a T-butoxide, so it's a very big base. This bulky base here could not get in and abstract these two protons. They just aren't accessible from the middle of the molecule here. Instead, they go after these less hindered beta protons, and that's what Hofmann observed. He said, if I use a bulky base, I can form the least stable alkene in preference to the most stable, and we call that the Hofmann product then. Zaitsev is the most stable alkene, Hofmann is the less stable alkene, and we do that by using a bulky. Let's look at some bulky bases. It turns out that bulky bases can either be my T-butoxide that we showed in the last slide, and that's a very common one, but we can also use some of these amines. You can see this NN diisopropylamine has these big two isopropyl groups in there, and I know that amines are basic. Here's another one which is NN disopropyl ethylamine, and here's the last one, triethylamine, often abbreviated T, and a fourth one down here. So when you see big amines in a reaction, think hindered base, or if you see a T-butoxide, think bulky hindered base and think Hofmann elimination reactions. Let's look at some product distributions based on the size of the base. If I look at a small base, this one would be an eth oxide, and if I look at the product mix based on the elimination reaction for this starting material, I find that I get a high percentage of the Zaitsev product and a lower percentage of the Hofmann product. If I start to increase the size of the base, so this is a fairly bulky base, I see that my Hofmann product increases and my Zaitsev product decreases, again because it's easier to abstract these hydrogens out here on this molecule. I could also add some more alkyl groups to my base, and what I notice is that my Hofmann product continues to increase. So here's a very, very bulky base, and I have 92% yield of the Hofmann product and only 8% yield of the Zaitsev product. As scientists were investigating elimination reactions, one phenomenon that they noticed was that if I used a fluoroalkyl halide, the product mix tended to favor the least substituted alkene, the Hofmann product, over the Zaitsev product in fairly substantial percentages. After a number of years of research, they were able to determine that the transition state for fluorine as a leaving group is actually carbanion-like. Because the fluorine is such a poor leaving group, that carbon in which we're removing the hydrogen is a little bit negative, and having an external negative charge is more stable than having a positive internal carbon. So my transition states for forming the Hofmann product right here is lower than forming the Zaitsev product. So it's based on arguments of the transition state stability, lower activation energies to get to this product than this one here. So let's look at the stability of carbocations and carbanions. So if I look at carbocations, the more substituted carbocations are more stable than the least substituted. It's just opposite for carbanions. And so in this case, if I have a more substituted carbanion, that's less stable than a methyl anion. So that explains, based on the transition state theory, that last slide where the fluorine leaving group promotes the Hofmann product. Let's look at and contrast the other halogens as leaving groups: iodine, bromine, chlorine, and fluorine. And let's just look at their product mix. So if I look at the most stable product here, meaning the Zaitsev product, if I use iodine, I promote the Zaitsev product because it goes more to a cation intermediate, whereas the fluorine down here at the bottom goes through a more anion intermediate and favors the Hofmann product. And you can see there's a gradual transition here between the two. So if I want Zaitsev product, I would actually choose iodine as my leaving group, or bromine. If I want the Hofmann product, I'm going to choose chlorine or even fluorine, even though this would be a much slower reaction here. So I can adjust my product mix not only by adjusting the reaction conditions, I can adjust the starting materials. Let's do a couple practice exercises where we're going to predict the elimination products of the following reactions. When two alkenes are possible, meaning the Zaitsev product or the Hofmann product, let's predict which one will be the major product. Let's look at 2-bromopentane reacting with sodium methoxide. Let's first just draw out the 2-bromopentane. I notice here that here is my alpha carbon. Here is one beta carbon with 3 hydrogens. Here is a second beta carbon with 2 hydrogens. I could either abstract any of these 5 hydrogens. Zaitsev would say if I have a small unhindered base, I'm going to form the more stable alkene, the more substituted one, and we do have a small strong base. So I'm going to favor abstracting these 2 protons, and in fact what I see experimentally is I see the internal alkene favored over the alkene that is at the end of the chain here. Notice I've drawn this squiggly line right here. That represents the fact that my alkene could either be in the E or the Z stereochemistry, cis or trans in this case also. Let's look at the second example. Let's redraw 3-bromo 3-methylpentane so we can get a view of that. Notice this is a tertiary alkyl halide. I have 3 beta hydrogens here. I have 2 beta hydrogens here and 2 beta hydrogens here. These 2 are identical because it is a symmetric molecule. I do in this case also have a small unhindered strong base, so I'm thinking Zaitsev's rule again. So if I predict the product, I'm going to predict that I'm going to remove either one of these 2 or one of these 2. And when I look at my product mix, that's what I find out. My product is the more substituted alkene. Again, I've drawn this squiggly line to represent the fact that I could get either the E or the Z stereoisomer. My minor product would be this alkene that's only disubstituted. If I look down here at the third example, I'm going to redraw 2-bromo 3-ethylpentane. If I look at this one, this happens to be a secondary alkyl halide. I'm going to now look for beta hydrogens. I have 3 out here and I have 1 here. I look at my base and it's a strong small base. Hydroxide is very small, and so I'm going to predict that I'm going to get the Zaitsev product in majority, and that's what we see experimentally. I see the more substituted alkene as being the major product, and the minor product would be the monosubstituted alkene. Why didn't I draw a squiggly line here? That's because these 2 products, these 2 groups out here on this side of the alkene are identical, so I do not have any stereoisomers in this case. Let's look at elimination reactions in cyclic compounds. So here I have a halogenated cyclohexane. I have a base, and my elimination product is cyclohexene. If I drew this alkyl halide in the chair conformation, I look at these and I see that my bromine is equatorial in this conformation and my hydrogen is equatorial. I could redraw that a little bit, so I could actually do the ring flip and find out that after I do ring flip, this is going to be axial and this is going to be axial, and they have to be in this axial orientation in order to be eliminated. This is easier seen if I draw that in the Newman projection. Here I have the bromine axial and the hydrogen axial. Those are anti-coplanar to each other. We often call these trans. Diaxial is another term that's often used to describe this relationship. So if I have them in the equatorial position, I cannot do an elimination reaction. But I know they can do a chair flip, and actually all the equatorials become axials. Once they are in the axial orientation, they can undergo an elimination reaction. Let's look at the stereochemistry of an elimination reaction. I can often look at the Fischer projection of a molecule that has 2 chiral centers. I know I have to do a rotation about a bond to get those antiperiplanar to each other. So when I do that, notice that my phenyl ring is sticking way in the back. And in this case, my phenyl ring is sticking in the front. My methyl group is sticking in the front here, and my hydrogen is sticking in the back. Once I do the rotation to get those antiperiplanar to each other, my resulting alkene ends up preferentially in that orientation. So in this case, I form the E stereoisomer because I have to go through this antiperiplanar orientation in order to do an elimination reaction. Let's look at the relative reactivities of alkyl halides, and let's contrast tertiary versus secondary versus primary alkyl halides. So if I look at these three different alkyl halides, the tertiary alkyl halides actually undergo elimination reactions, E2 reactions, at a faster rate than secondary than do primary alkyl halides. Let's look at the following chemical reaction and explain why I only see one product and not three products. Because if I look at the starting materials, let's see, here's my alpha carbon. I have one beta hydrogen here. I have a second beta hydrogen, and I have a third beta deuterium, which is the isotope of hydrogen. So I might predict I would form three different products, but in fact I only see one. That is easier seen if I were to redraw my reactant in the chair conformation. So here I've drawn it, and I've drawn my bromine in the axial position. And when I look at that, I only have one hydrogen, in this case the deuterium, which is transdiaxial to the halogen, and that's the only one that can be abstracted to do an elimination reaction. These two are in the equatorial position, these two beta hydrogens, so that does not undergo elimination. Accounting for my only one product that's formed, removing this deuterium, which is anti, and it's diaxial from that halogen there. So this would actually be a dehydrohalogenation reaction too. This is a strong base, which means I'm going to favor my Zaitsev product, and it's small. There is a special elimination reaction that scientists have discovered, and that's the elimination of vicinal dihalides, specifically vicinal dibromides. So if I were to look at this molecule, which is 1,2-dibromo 1,2-diphenyl ethane, I redraw that in the Newman projection. I can draw one of the most stable conformations where my phenyl groups are on opposite sides and my bromines are on opposite sides. In other words, they're anti to each other. If I throw in some sodium iodide, it tends to attack the bromine, and I undergo an elimination reaction. So this is a special one. Iodine anion removes vicinal dibromides to form an alkene. Again, the bromides must be anticoplanar to each other. I could use either sodium iodide, or in some cases we found another reagent that does the same thing, just zinc metal. So I could either use iodide or I could use zinc to eliminate vicinal dibromides, bromines on two adjacent carbons, to form alkene. So let's look at this and let's predict the products. If I look at this substrate, I notice it's a vicinal dihalide. I've thrown in sodium iodide, which is a source of iodide, and I put in some acetone. That is just a solvent, so that's a polar aprotic solvent. I know that this reaction does elimination. I've oriented it so that I get these two bromines antiperiplanar to each other, which means I'm going to have my resulting alkene is going to be the E stereoisomer, because I have to orientate my methyl group and hydrogen and a methyl group and hydrogen to form this orientation. This is called a dehalogenation reaction, a dehalogenation of vicinal dibromides. and it is an E2 reaction also. Let's do another practice exercise. Let's see. Let's just name this reaction. If I look at it, it looks like it's going to be a dehydrohalogenation because I'm removing hydrogen and bromine. This is an elimination reaction, and it's undergoing a concerted reaction, so it's going to be an E2 reaction. We've now discussed two different types of elimination reaction, E1 and E2. Let's look at the factors that actually promote one over the other, and then let's also look at the characteristics. So if I look at E1 reactions, they usually are favored by weak bases, whereas E2 reactions are favored by strong bases. The solvent, for E1 I need a good ionizing solvent. Typically that's a polar protic solvent. E2 is a little more forgiving. I have a wide variety of solvents that are favored. Most of the time we use a polar aprotic solvent like acetone. If we look at the substrates, a tertiary alkyl halide is favored over a secondary for an elimination. That's because I go through a carbocation and the tertiary carbocation is more stable. For an elimination II reaction, the tertiary is more favored over the secondary, which is more favored over the primary, but you can do eliminations with all three of them using the E2 mechanism. Leaving group, both of them require a good leaving group, a good alkyl halide. If we look at the characteristics of the two different types of elimination reactions, E1 is first order. It's only dependent on the alkyl halide forming the carbocation, whereas the E2 reaction is dependent on both the alkyl halide and the base forming a transition state. The orientation for E1 reactions is the most substituted product is formed, and that is true for E2 also. This is the Zaitsev product. If I look at the stereochemistry, because E1 reactions go through a carbocation, I form no special stereochemistry. E is not favored over Z. However, if I look at E2 reactions, because I have to go through this antiperiplanar or coplanar transition state, I'm going to favor the more stable transition state. One of the drawbacks of E1 reactions are that rearrangements are common. E2, they are impossible because I need to go through this transition state with a very specific orientation. So this is contrasting E1 versus E2. Let's do a practice exercise where we propose chemical reagents to prepare 2-methylpropene from 3 different starting materials. In the first case here, I have a tertiary alkyl halide. I'm thinking elimination reaction. I'm going to look for beta hydrogens here, and I have 9 of them, 3 here, 3 here, and 3 here. Since this is a tertiary alkyl halide, I can actually just use common methanol and heat. This is a weak nucleophile. So what type of reaction would this be? That would be an E1 reaction to form 2-methylpropene. If I look here at this starting reactant, I notice that I have a tertiary alcohol. OH, my hydroxyl group, is a poor leaving group, so I need to make it a good leaving group. So I add acid. So I protonate that, making it a good leaving group. My water acts as a base. If my water is a base, that's solvent again. This is also going to be an E1 reaction. If I look down here, I notice that I have vicinal dihalides. We have a special reaction for that. I take sodium and iodine with some acetone to do an elimination of these vicinal dihalides. This is an E2 reaction. I could have used zinc and acetic acid also. That's another set of reagents that will actually remove vicinal dihalides, vicinal dibromides from each other.